The universe is an incredibly vast, intricate tapestry woven with countless stars, planets, galaxies, and other celestial wonders that continue to baffle and inspire scientists and explorers alike. Picture an endless expanse filled with millions of stars and planets, each distinct, each harboring unique features and unimaginable secrets. Beyond the serene beauty of the night sky we see from Earth, the universe harbors realms so alien, so extreme, that they defy our earthly understanding of what planets and stars should be. When we think about these celestial bodies, many envision peaceful worlds with tranquil atmospheres and stable, life-supporting conditions. However, the reality is far more complex and often terrifying. Beyond our solar system lie planets with conditions so extreme that they stretch the boundaries of what we believe is possible. Imagine a place where rain doesn't consist of water but glass, and it falls sideways, slicing through the air at thousands of kilometers per hour due to the force of violent winds. These planets may be cloaked in constant darkness, with atmospheres so thick and air pressure so high that it would crush a human being in an instant, long before they could even set foot on the surface. In other regions, there exist rocky worlds entirely covered in seas of molten lava, their skies blazing red under the unrelenting glare of a nearby star. The diversity of these planets is a reminder of how little we know about the universe. The planets in our own solar system, Earth, Mars, Venus, and the gas giants like Jupiter and Saturn, are remarkable enough. But these are just a tiny fraction of what's out there. Scientists have only recently begun to peer beyond our solar system to identify and study exoplanets, planets orbiting stars other than our own Sun. The more we learn about these distant worlds, the more we realize that the possibilities are limitless. Take, for instance, giant gas planets like Jupiter but with much more extreme atmospheres. These are places where the pressure is so immense that even the hardiest spacecraft we can build would be crushed before it could relay data back to Earth. The storms on these planets are perpetual, massive whirlwinds that dwarf anything we've ever seen. One such example is a planet where winds reach speeds of over 5,400 miles per hour, almost 7 times faster than the fastest winds on Earth. In comparison, hurricanes on Earth seem almost gentle. But why explore these alien worlds? What can we gain from learning about planets that, at first glance, seem utterly inhospitable and even hostile to life? The answer lies in our quest to understand the full range of possibilities in our universe. By studying these extreme environments, we can unlock secrets about the fundamental forces and processes that shape planets and stars. These findings can enhance our understanding of how planets form and evolve, providing us with clues about our own planet's past, present, and future. Additionally, these studies contribute to the ongoing search for life beyond Earth. While conditions on some of these planets are certainly far too extreme for life as we know it, exploring the limits of what a planet can be helps us expand our thinking about where life might arise and survive. The discoveries made by space telescopes and observatories, such as the Kepler Space Telescope and the James Webb Space Telescope, have transformed our understanding of the universe's composition. These technologies allow us to detect planets that orbit their stars at dizzying speeds, sometimes completing an entire orbit in just a few days or hours. This close proximity means that their temperatures are extraordinarily high, sometimes hot enough to vaporize metals. In contrast, we've also found planets that are so distant from their stars that temperatures plummet to hundreds of degrees below zero. These discoveries suggest that planetary diversity is much greater than previously thought, and that the Goldilocks zone, or the habitable zone around a star, may look different on each planetary system. Imagine a world where the surface is a fiery landscape of molten rock, perpetually bubbling and churning under a sky painted with hues of red and orange due to the intense heat from a nearby star. For instance, a planet such as Kepler-10b, a rocky planet located around 560 light-years away, has temperatures so high that its surface is thought to be covered in a boiling ocean of lava. Meanwhile, another planet, 55 Cancri e, may contain an interior with carbon-rich minerals under such pressure that it could create a diamond crust, leading scientists to dub it the Diamond Planet. This fascination with the universe's extremes isn't limited to planets alone. Even stars come in a staggering variety. While we are familiar with the yellow-white glow of our Sun, other stars can range from red dwarfs to blue giants, each type indicating different temperatures, compositions, and lifespans. For instance, red dwarfs are smaller and cooler than our Sun but are incredibly long-lived, potentially providing stable environments for billions of years. The intense energy from blue giants, on the other hand, burns fast and hot, but they live only for a short time before dying in spectacular supernova explosions. Each discovery we make opens new questions and challenges existing theories about planetary science and astrobiology. By studying planets with incredibly high temperatures, freezing atmospheres, or extraordinary pressures, scientists can develop new models and simulations to predict planet formation and behavior. These models allow us to experiment with different conditions and see what kind of planets could theoretically exist. This is not just academic interest, it has real implications for how we understand the history and future of Earth and its place within the cosmic order. The exploration of these planets is also a deeply humbling experience. Each finding emphasizes that our home, Earth, is a rare and precious world. Despite the harsh environments we've encountered on other planets, Earth exists in a delicate balance that allows for liquid water, a stable atmosphere, and temperatures that support life. Understanding the harsh realities of other planets underscores just how unique and fragile this balance is, reminding us of the importance of protecting our environment and safeguarding the conditions that make life possible here. As we continue to explore, the purpose of our journey remains grounded in the pursuit of knowledge. Each new world we discover provides valuable data that can change our understanding of what's possible in the cosmos. Whether it's a gas giant with permanent night and day sides or a planet with a surface so reflective it appears almost invisible, every discovery enriches our appreciation of the universe's complexity and beauty. In this journey across the cosmos, the extreme conditions we encounter also serve as a cautionary tale. They remind us that while we may dream of colonizing other planets, it will require overcoming immense challenges. The hostile atmospheres, crushing pressures, and relentless radiation of many exoplanets show just how rare it is to find a place like Earth. However, with each breakthrough, we inch closer to perhaps one day finding another world that may be just right for life or even learning to adapt ourselves to these extremes. As telescopes grow more powerful and our grasp of planetary sciences expands, humanity stands on the threshold of an extraordinary era in exploration. No longer limited to observing our immediate cosmic neighborhood, we are reaching out across vast distances, exploring planets light years away, and uncovering the complexities of planetary systems that were once thought to be beyond our reach. These advancements aren't just broadening our understanding of the cosmos, they are fueling our imagination, stirring visions of actually visiting these distant worlds one day. The question is no longer if we can study planets around other stars, but rather how close we are to physically exploring them. Today, our most advanced telescopes, such as the James Webb Space Telescope, allow us to peer into the atmospheres of exoplanets, detecting water vapor, methane, and other chemicals that could hint at conditions suitable for life. We can analyze these atmospheres to learn about planetary climates, surface compositions, and even potential biosignatures, indicators of life that may exist elsewhere in the universe. Each discovery moves us closer to understanding the diverse types of environments that exist beyond Earth, from hot Jupiters with scorching temperatures to potentially habitable worlds in the Goldilocks zones of their stars. This knowledge provides a crucial foundation for future exploration, giving us a roadmap of potential destinations that may one day become targets for probes or even human missions. Advancements in robotic explorers have already enabled us to send sophisticated instruments to the far reaches of our own solar system. Spacecraft like Voyager, New Horizons, and Pioneer have provided invaluable data from distant worlds like Pluto and the outer planets, revolutionizing our understanding of the solar system's outer regions. These missions serve as proof that we can build machines capable of withstanding the harsh conditions of deep space, operating autonomously across distances where communication takes hours, if not days. They've set the stage for increasingly ambitious exploration, as scientists and engineers work to create even more advanced space probes that could travel to neighboring star systems. The concept of sending probes to the nearest stars is no longer purely theoretical. Projects like Breakthrough Starshot are actively investigating the feasibility of launching small, light-propelled probes to Alpha Centauri, our closest star system. These probes, propelled by powerful laser beams from Earth, could reach speeds up to 20% of the speed of light, potentially making the journey to Alpha Centauri in just over 20 years. While they won't carry humans, these tiny probes could transmit data back to Earth, providing the first close-up images of exoplanets around another star. This type of mission would mark a monumental step forward in our journey toward interstellar exploration, as we venture beyond the solar system to gather direct evidence of other planetary systems. However, the dream of human exploration beyond our solar system remains more complex and distant. The challenges of interstellar travel are immense, the distances involved are staggering, and even our fastest spacecraft would take tens of thousands of years to reach the closest stars. But advances in propulsion technology, artificial intelligence, and life support systems continue to bring us closer to achieving this goal. Scientists are exploring new propulsion concepts like nuclear fusion or antimatter engines, which, while still in their infancy, could one day allow for speeds far beyond what is currently possible. If these technologies develop as some researchers hope, humanity might eventually overcome the vast distances that separate us from other stars, opening up the possibility of crewed missions to explore alien worlds. Until the day we can set foot on these distant planets, our telescopes and robotic explorers remain essential as our eyes in the universe, extending our vision across unimaginable distances. Through their lenses, we can observe the birth and death of stars, the formation of planets, and the cosmic forces that shape galaxies. They bring back images and data that allow us to study the physics of the cosmos, the evolution of planetary systems, and the conditions that might allow life to flourish elsewhere. Each new discovery adds another piece to the puzzle of our universe, bringing us closer to understanding the forces that govern everything from the tiniest particles to the largest galaxies. This new era of exploration holds profound implications for our understanding of our place in the cosmos. As we uncover more about distant planets and the potential for life beyond Earth, we are reminded of both the uniqueness of our planet and the possibilities that await us. The knowledge we gain from these explorations may help us understand the conditions that led to life on Earth, guiding us in the search for other habitable worlds and perhaps even showing us how to protect and preserve our own planet. Our advances in technology and planetary science bring us ever closer to realizing the dream of interstellar exploration. While there is still much work to be done, the continued development of powerful telescopes, advanced probes, and revolutionary propulsion systems gives us hope that humanity will one day reach the stars. Until that time, we continue to push the boundaries of our knowledge, seeking answers to the age-old question of whether we are alone in the universe and what lies beyond the horizon of our world. Each new discovery, each technological leap, moves us one step closer to the stars, fulfilling our enduring desire to explore and understand the cosmos. This quest is about far more than simply discovering new planets. It's about challenging our assumptions, expanding our horizons, and nurturing the eternal curiosity that drives us to explore. The universe is our final frontier, and each step we take brings us closer to understanding our place within it. In the vast, seemingly endless cosmos, every discovery tells a story, every planet has secrets, and every extreme environment tests the limits of our imagination and understanding. With each new finding, we become not only better scientists but also better stewards of our world, equipped with a greater appreciation for the delicate life-supporting cradle that we call home. In the vast expanse of our universe, some planets defy the very rules we assume to be true about celestial bodies. Among these are dark exoplanets, mysterious worlds with properties so extreme that they challenge our understanding of what a planet can be. These planets exhibit characteristics that seem more fitting for a science fiction novel than reality. Two remarkable examples are TRES-2b and 55 Conchoree e, each unique in its own terrifying and fascinating way. TRES-2b, located in the constellation Draco, is one of the darkest planets ever discovered. Astronomers identified this planet in 2006 using the transit method, which observes how a star's light dims slightly when a planet passes in front of it. This discovery was significant because TRES-2b has a remarkably short orbit, circling its star in only 2.5 days due to its extreme proximity, about 3 million miles away, far closer than Mercury is to our Sun. This closeness subjects TRES-2b to intense heat, pushing its surface temperature above 1,800 degrees Fahrenheit. What sets TRES-2b apart isn't just its high temperature but its extremely dark appearance. This planet reflects less than 1% of the light that hits it, making it darker than coal, and by far the darkest known planet. The reason for this eerie darkness lies in its atmospheric makeup, which includes elements like vaporized sodium and potassium. These elements are highly light-absorbing, meaning they trap most of the incoming light rather than reflecting it. The atmosphere of TRES-2b lacks clouds that would normally scatter light, creating a thick, opaque layer that absorbs nearly all light and makes the planet appear like an inky black sphere. Despite its darkness, TRES-2b is not entirely invisible to astronomers. The planet emits a faint red glow, a result of the immense heat it experiences due to its proximity to its star. This glow, though dim, adds an eerie, almost hellish allure to TRES-2b. Imagine standing on this dark world, where the faint crimson radiance is the only sign of the planet's otherwise blackened surface. The high temperatures on TRES-2b are largely maintained by its tidal locking with its star, a phenomenon where one side of the planet is always facing the star while the opposite side remains in perpetual darkness. This creates a severe temperature contrast between the day side and night side, likely giving rise to fierce winds and chaotic weather patterns that are unlike anything seen on Earth. The study of TRES-2b provides scientists with invaluable data on planetary atmospheres and exoplanet diversity. Observing how light-absorbing elements interact in TRES-2b's atmosphere helps researchers develop models to predict atmospheric behavior on other planets. This knowledge is particularly useful as we continue to discover new gas giants that orbit close to their stars, many of which may have similarly unique atmospheric compositions. TRES-2b also stands as a testament to the universe's diversity, showing that not all planets follow the norms we expect. This planet offers a glimpse into how wildly different conditions can be across our galaxy, opening our minds to the variety of worlds that exist beyond our solar system. Then there's 55 Conchoree e, another remarkable and vastly different exoplanet that reveals just how unpredictable the universe can be. Located approximately 40 light-years away in the constellation Cancer, 55 Conchoree e is classified as a super-Earth, meaning it is a rocky planet that is much larger than Earth. With a mass 8 times that of Earth and a diameter nearly twice as large, 55 Conchoree e is an immensely dense world. It orbits its host star, 55 Conchoree a, at an incredibly close distance, completing an orbit in just 18 hours, a stark contrast to Earth's 365-day orbit around the Sun. This extreme proximity places it among the category of ultra-short-period planets, which experience constant exposure to stellar radiation, making them some of the hottest exoplanets observed. What makes 55 Conchoree e so fascinating is its possible diamond composition. Scientists have theorized that this planet might contain high levels of carbon, which, under intense pressure, could transform into diamond. If true, 55 Conchoree e would be a literal diamond in the cosmos, a shimmering jewel among exoplanets. This hypothesis is based on observations that suggest the planet is carbon-rich and contains other elements that could support the formation of diamond. If this theory holds, then 55 Conchoree e could have a crystalline structure that sparkles like a diamond, albeit in the oppressive, deadly heat of its star. Beyond its unique composition, 55 Conchoree e has an extreme atmospheric state. Unlike Earth, whose atmosphere is composed primarily of nitrogen and oxygen, 55 Conchoree e's atmosphere could be dominated by heavy gases like hydrogen, and potentially dangerous compounds like hydrogen cyanide, a marker of carbon-rich environments. The atmosphere likely exists in a supercritical fluid state, a state that blurs the line between liquid and gas. In this form, the gases would flow like a fluid across the planet, creating an environment that is completely foreign to anything we know on Earth. The intense heat on 55 Conchoree e, which exceeds 4,000 degrees Fahrenheit, means that any atmosphere present is unlike anything in our solar system, adding to its allure as a world of unimaginable extremes. 55 Conchoree e, a super-Earth located just 40 light-years away, orbits its star so closely that it completes a full orbit in just 18 hours. Because of this extreme proximity, it is tidally locked to its star, meaning that one side of the planet is in permanent daylight while the other side remains in eternal darkness. This setup creates a dramatic temperature contrast between the two hemispheres, with the star-facing side experiencing blistering heat while the dark side remains significantly cooler. This situation, known as tidal locking, has a profound impact on the planet's climate and weather patterns. The stark temperature difference between the day and night sides of 55 Conchoree e likely drives supersonic winds across the planet. On Earth, temperature contrasts can lead to strong winds, but the effect is far more intense on 55 Conchoree e due to the extreme heat on the day side. These winds are thought to transport some of the heat from the star-facing side to the cooler night side, attempting to balance the planetary temperatures. However, the intensity of these winds and the scale of heat distribution create weather patterns that are far beyond anything seen on Earth, where our atmosphere is relatively calm by comparison. The atmospheric behavior on 55 Conchoree e defies Earth-based meteorological models because our models are designed for a rotating planet with day and night cycles. Tidal locking creates an environment with constant, unchanging conditions on each side, leading to a unique and intense atmospheric circulation system. Scientists studying 55 Conchoree e can learn much about how tidal locking affects planetary atmospheres and how extreme conditions might shape the climate on other exoplanets. Understanding the dynamics of this super-Earth broadens our perspective on planetary climates, especially for worlds that orbit close to their stars, and helps develop models for predicting the atmospheric behavior of other tidally locked exoplanets. The mystery surrounding 55 Conchoree e's composition and environment has made it a prime candidate for future observational studies. With the upcoming deployment of more advanced telescopes, such as the James Webb Space Telescope, scientists hope to gather detailed information about its atmospheric composition, surface conditions, and geological activity. These observations could confirm or challenge the diamond hypothesis and offer insights into the planet's evolution. The study of 55 Conchoree e and other similar planets also pushes the boundaries of planet formation theories. By examining worlds with high carbon content, astronomers are exploring the diversity of planetary types in our galaxy, from rocky planets to those rich in metals or carbon. The discovery of TRES-2b in 55 Conchoree e marks significant progress in our understanding of exoplanets, each unique and offering valuable insights into the complexity of planetary systems. Together, they exemplify the universe's capacity for surprise, challenging the limits of our imagination, and demonstrating the wild extremes that planetary environments can reach. These planets serve as reminders of how little we know about the universe and the vast diversity that awaits us as we continue to explore the cosmos. Among the most exciting pursuits in the study of exoplanets is the search for planets within habitable zones, areas around stars where conditions may allow for liquid water, a key ingredient for life as we know it. Scientists have identified several exoplanets within these zones, yet only a few stand out as promising candidates for further exploration. Two of the most intriguing examples are Gliese 581c and Proxima Centauri b, planets orbiting relatively nearby stars. Both of these exoplanets lie within or near the habitable zones of their host stars, hinting at the potential for environments that might sustain life. Gliese 581c, discovered in 2007, orbits a red dwarf star called Gliese 581, located about 20 light-years away in the constellation Libra. This planet holds a unique place in the search for extraterrestrial life because it exists within the habitable zone of its star, where temperatures could theoretically allow for liquid water under the right conditions. However, Gliese 581c is quite different from Earth in both size and gravity. It has a mass approximately 5.5 times that of Earth and is categorized as a super-Earth. The increased gravity on Gliese 581c would have significant effects on its atmosphere, possibly creating a thick layer of gases that could retain heat and potentially allow for water to exist in liquid form on the surface. One of the defining features of Gliese 581c is that it is likely tidally locked with its star. In a tidally locked planet, one side is always facing the star in perpetual daylight, while the opposite side remains in eternal darkness. This setup results in extreme temperature variations across the planet, with one side potentially scorching hot, and the other freezing cold. However, some scientists believe that there could be a twilight zone between the day and night sides where temperatures might be moderate enough to support liquid water. This twilight zone could potentially become a band of habitability around the planet, a region where water could exist in rivers, lakes, or even shallow seas, creating a unique environment unlike anything we see on Earth. The potential for a stable climate on Gliese 581c hinges on atmospheric circulation, or the ability of the atmosphere to distribute heat across the planet. If Gliese 581c has an atmosphere that can circulate heat effectively, it might prevent the drastic temperature disparities caused by its tidal locking. For instance, winds could transport warm air from the sunlit side to the dark side, evening out temperatures across the surface. This process would allow for more stable temperatures, especially in the twilight zone, where conditions might resemble the cool, temperate climates found on Earth. Such atmospheric dynamics would be crucial for any life forms trying to adapt to the planet's extreme environmental challenges. The atmospheric composition of a planet is crucial when assessing its potential to support habitability, especially for planets like Gliese 581c, which orbits a red dwarf star in a region where liquid water could potentially exist. If Gliese 581c possesses a thick atmosphere with a high concentration of greenhouse gases, such as carbon dioxide or methane, it would create a warming effect by trapping heat, which could keep the surface temperatures warm enough to sustain liquid water. This greenhouse effect would be especially beneficial on a tidally locked planet like Gliese 581c, where one side remains in perpetual darkness. The retained warmth could extend to the dark side, moderating the extreme temperature differences and possibly creating stable, habitable zones even away from the star-facing side. On the other hand, if Gliese 581c lacks a substantial atmosphere, or if its atmosphere is thin, the planet would lose heat rapidly on its night side, leading to extreme cold. Without sufficient greenhouse gases, the temperatures on the dark side would likely drop too low for liquid water to remain stable, significantly reducing the likelihood of habitable conditions across the entire planet. In this scenario, only the star-facing side might retain warmth, and even then, the narrow range where temperatures would allow for liquid water would be restricted to regions directly exposed to sunlight. Scientists are eager to investigate Gliese 581c's atmospheric properties, and upcoming telescopes and missions with advanced spectroscopic capabilities could reveal more about its atmospheric composition. By analyzing the gases present in Gliese 581c's atmosphere, researchers can better understand its climate dynamics and assess the likelihood of water stability, particularly on the planet's night side. Discovering whether Gliese 581c has a thick or thin atmosphere will be a key factor in determining its habitability and will provide valuable insights into the conditions needed to support life on planets orbiting close to red dwarf stars. Another fascinating candidate within the habitable zone is Proxima Centauri b, a planet that orbits Proxima Centauri, the closest known star to our Sun, located just 4.24 light-years away. Proxima Centauri b's proximity makes it an enticing target for study, as it provides a rare opportunity to examine a potentially habitable world close to Earth. This planet, discovered in 2016, has a mass similar to Earth, which has fueled interest in its potential for life. However, Proxima Centauri b faces a unique set of challenges that make its environment far from ideal for sustaining life as we know it. One major obstacle is that Proxima Centauri, like many red dwarf stars, emits powerful stellar flares that can periodically bombard the planet with high levels of radiation. These flares are not only intense but also frequent, potentially posing a significant threat to any atmosphere Proxima Centauri b might have. If these flares strip away the planet's atmosphere, it would leave the surface exposed to harsh radiation, making it nearly impossible for liquid water to remain stable, let alone for life to flourish. Despite this, some scientists believe that Proxima Centauri b could still have a way to protect itself from these radiation bursts. The magnetic shield hypothesis suggests that if Proxima Centauri b has a strong magnetic field, similar to Earth's, it could deflect a significant portion of the radiation from its host star. Earth's magnetic field acts as a shield, protecting us from the Sun's solar wind and high-energy particles. If Proxima Centauri b possesses a comparable magnetic field, it could maintain an atmosphere capable of supporting liquid water. This protective layer would be essential for any potential life on the planet, as it would create a stable environment on the surface, protecting it from the dangers posed by its star's activity. The possibility of microbial life on Proxima Centauri b is particularly exciting for astrobiologists. Even if the planet is subject to radiation and intense flares, certain types of life forms, such as extremophiles, could potentially survive in such environments. Extremophiles are organisms that thrive in extreme conditions, from the high radiation environments around nuclear reactors to the icy, pressurized depths of Earth's oceans. On Proxima Centauri b, life might find refuge underground or in environments shielded from the star's radiation, just as extremophiles on Earth survive in some of the planet's most inhospitable regions. If liquid water exists on Proxima Centauri b, it could support microbial ecosystems that are adapted to high radiation levels, offering tantalizing clues about the adaptability of life. Both Gliese 581c and Proxima Centauri b embody the promise and complexity of habitable zones around other stars. They serve as examples of how life-sustaining conditions may exist even under extreme circumstances, where tidal locking or radiation would make survival challenging. These exoplanets also underscore the diversity of environments that can potentially support life. On Earth, we have learned that life can adapt to conditions ranging from scorching deserts to freezing tundras. Studying planets like Gliese 581c and Proxima Centauri b challenges us to broaden our understanding of habitability, encouraging scientists to redefine the conditions under which life could arise. The future study of these planets relies on advanced observational technologies that can analyze their atmospheres, detect signs of water, and potentially identify biosignatures, or indicators of life. Spectroscopy, for instance, allows scientists to examine the light that passes through a planet's atmosphere, revealing its composition by identifying gases such as oxygen, carbon dioxide, and methane. The presence of these gases, especially in certain ratios, could indicate biological processes. Upcoming missions, including those by the James Webb Space Telescope, promise to provide detailed information about the atmospheric conditions on Gliese 581c and Proxima Centauri b, bringing us closer to answering the age-old question, are we alone in the universe? By studying habitable zones and the potential for water on planets like Gliese 581c and Proxima Centauri b, scientists are not only seeking to understand where life might exist but also learning more about the formation and evolution of planetary systems. Each discovery adds to our knowledge of how common, or rare, habitable worlds may be. It also offers a humbling reminder of Earth's uniqueness, and the delicate balance that sustains life here. Gliese 581c and Proxima Centauri b, with their unique environments and challenges, inspire us to continue exploring, to push the boundaries of our knowledge, and to remain open to the possibility that life, in some form, may exist beyond Earth. As we continue to discover exoplanets, it becomes evident that some worlds possess unusual features that defy traditional planetary classifications and raise profound questions about planet formation and the dynamics of solar systems. In this chapter, we'll explore two unique exoplanets, Pymensae C and Fomalhaut b, each of which offers intriguing insights into the complexity of planetary systems and the mysteries that remain in understanding how these systems evolve. Pymensae C, often referred to as a super-Earth, is located around 60 light-years away in the constellation Mensa. This planet exists in a dynamic planetary system that includes Pymensae b, a much larger gas giant. The dual presence of a super-Earth and a gas giant in the same system provides a unique setup for studying the diversity and interaction of planets within a single star system. Pymensae C is thought to have a mass around 4.82 times that of Earth, making it significantly larger than our planet but still much smaller than a typical gas giant. Such planets, classified as super-Earths, are of great interest to astronomers because they fall into a category that doesn't exist within our own solar system, offering insights into planetary types and formations that we can't observe up close. One of the most captivating aspects of Pymensae C is its atmosphere. Early observations have suggested that this exoplanet could have a thick atmosphere, possibly containing elements and compounds essential for life, such as water vapor. Studying its atmosphere in detail could provide insights into the planet's potential for habitability and help scientists refine their models for determining the conditions necessary for life. Atmospheric studies of Pymensae C could also shed light on the composition of super-Earths more broadly, answering questions about whether these planets are generally rocky, watery, or more akin to gas-dominated worlds. Detecting water vapor in its atmosphere, for example, would be a major breakthrough, indicating that the planet might have been, or could still be, capable of supporting liquid water, which is crucial for life as we know it. However, the presence of Pymensae b in the same planetary system adds an additional layer of complexity. This gas giant's large mass and gravitational influence could impact Pymensae C's orbit, potentially affecting its climate and atmosphere. If Pymensae b's gravitational pull were strong enough to create tidal forces on Pymensae C, this could generate heat within the planet, affecting its atmosphere and possibly maintaining liquid water even if the planet itself is relatively distant from its star. Studying Pymensae C within this dual planet system allows scientists to observe how a super-Earth behaves under the influence of a gas giant, offering a fascinating case study in multiplanetary interactions and the range of planetary compositions that can exist within a single system. The Pymensae system's potential for atmospheric diversity and complex gravitational interactions provides invaluable data for exoplanetary science, helping to refine our understanding of planetary formation and evolutionary dynamics. Scientists are particularly eager to learn how Pymensae C's atmosphere has developed in the presence of a gas giant and what this means for other planetary systems where super-Earths and gas giants coexist. Each new finding about this system adds to a broader picture of the varied architectures of planetary systems in our galaxy, contributing to a growing catalogue of unusual planetary features and interactions. In contrast to Pi Mensae C, which has solid evidence as a planet, Fomalhaut B presents one of the more unusual and debated discoveries in the study of exoplanets. Fomalhaut B initially made headlines when it became one of the first exoplanets to be directly imaged by the Hubble Space Telescope in 2008. Located in the constellation Piscis Austrinus, Fomalhaut B orbits the star Fomalhaut, one of the brightest stars in the sky and situated about 25 light-years from Earth. At the time, the observation of Fomalhaut B was a groundbreaking achievement because it provided a visual confirmation of an exoplanet, which is a rare accomplishment due to the immense distance and the faint light of most exoplanets compared to their host stars. However, the initial excitement surrounding Fomalhaut B quickly became tempered by a debate over its true nature. Subsequent observations of Fomalhaut B did not align with typical characteristics of planets. For one, it lacked infrared emissions, which would indicate the presence of heat. Planets, especially those orbiting relatively close to their stars, generally emit detectable levels of infrared radiation, making this absence a significant anomaly. Furthermore, as scientists continued to observe Fomalhaut B, they noticed that it seemed to change position and even shape in successive images, a phenomenon that doesn't fit with the expected behavior of a planet on a stable orbit. These observations led some researchers to suggest that Fomalhaut B might not be a planet at all but rather a dust cloud resulting from a massive collision between two icy bodies. In this scenario, Fomalhaut B would be the debris field left behind by a high-speed collision, which could explain why it doesn't emit infrared radiation and why it appears inconsistent in images taken over time. Such a collision would have been an intense, catastrophic event, creating a vast, expanding cloud of dust that could easily be mistaken for a planet at first glance. If true, Fomalhaut B would represent one of the first observed instances of an interstellar collision remnant, providing unique insight into the violent processes that can shape planetary systems and debris fields. The debate surrounding Fomalhaut B underscores the complexities and limitations of current exoplanet detection methods. Initially, direct imaging seemed like the definitive way to confirm the existence of exoplanets. However, the case of Fomalhaut B shows that even with visual evidence, it can be difficult to distinguish between actual planets and other phenomena, such as dust clouds or transient cosmic events. This ambiguity has led astronomers to refine their techniques for analyzing exoplanetary candidates, employing spectroscopic analysis to identify chemical compositions and other physical characteristics that might distinguish a planet from a debris field or other celestial object. The implications of Fomalhaut B's debated nature extend far beyond its classification as a planet or dust cloud. If Fomalhaut B is indeed a collision remnant, it would raise new questions about the stability of planetary systems and the frequency of collisions in other solar systems. This discovery would suggest that debris fields could be more common around stars with young or dynamic planetary systems, where gravitational interactions frequently lead to destructive encounters. Observing such debris fields can provide valuable information about the history of planetary systems, helping scientists piece together how planets, moons, and other bodies form, collide, and sometimes disintegrate over time. Ultimately, the study of Pi Mensae C and Fomalhaut B represents the spectrum of unusual exoplanetary features that astronomers are beginning to uncover. While Pi Mensae C challenges us to consider the atmospheric and gravitational dynamics of super-Earths in multiplanetary systems, Fomalhaut B invites us to question our assumptions about what we consider a planet and to investigate the potential for destructive events within planetary systems. Together, they highlight the diversity and complexity of exoplanets and their environments, reminding us that the universe is filled with surprises that defy simple categorization and see. The universe is home to an astonishing array of planets, some of which defy conventional understanding with their ancient origins or peculiar characteristics. In this chapter, we'll explore two particularly enigmatic exoplanets, Methuselah, HD 140283, and WASP-12b. Both planets offer unique glimpses into the history and future of the cosmos, one through its extraordinary age and the mysteries of its existence, the other through its strange shape and inevitable fate. Methuselah, also known as HD 140283, is an ancient star that lies approximately 190 light-years from Earth in the constellation Libra. Often referred to as the Methuselah star due to its incredible age, this celestial body has challenged astronomers with a cosmic mystery. It appears to be older than the universe itself. Scientists have estimated Methuselah's age to be around 14.5 billion years, while the age of the universe is generally agreed upon as 13.8 billion years, based on measurements from the cosmic microwave background radiation and expansion rates. This seeming paradox has forced astronomers to refine their methods of age calculation and to question their assumptions about the early universe. The process of determining Methuselah's age relies on a combination of factors, including its metallicity, a measure of the star's composition, specifically the presence of elements heavier than hydrogen and helium. In stellar terms, metals include elements like oxygen, carbon, and iron, which are synthesized in the cores of stars and dispersed through supernova explosions. Methuselah has an extremely low metallicity, meaning it contains very few heavy elements, which is a strong indicator that it formed in the early stages of the universe, before these elements became common. Such stars are classified as population II stars, distinguished by their age and scarcity of metals. The lower the metallicity, the older the star is likely to be, as it would have formed when the universe had not yet been enriched by successive generations of stellar nucleosynthesis. In addition to metallicity, astronomers also study Methuselah's stellar movement to estimate its age. Methuselah moves through the galaxy at a high velocity relative to nearby stars, suggesting it is part of an ancient Methuselah moves through the galaxy at a high velocity relative to nearby stars, suggesting it is part of an ancient population of stars orbiting the galactic halo. Its motion and position further support the idea that it originated in the early universe. To refine age estimates, scientists use stellar evolution models that take into account Methuselah's temperature, brightness, and metal content, cross-referencing these factors to derive a probable age. Despite these methods, the estimated age of 14.5 billion years continues to pose a paradox, pushing astronomers to refine their models and seek explanations that align with current cosmological understanding. Methuselah's estimated age is around 14.5 billion years, which is perplexing because it suggests that this star may have formed before the Big Bang, the event that is believed to have created the universe about 13.8 billion years ago. This age discrepancy has led scientists to rethink some fundamental assumptions about the universe's early stages and the methods we use to measure cosmic age. One key area affected by this mystery is our understanding of cosmic expansion rates, specifically those described by the Hubble constant. The Hubble constant is a value that represents how fast the universe is expanding. It was named after the astronomer Edwin Hubble, who discovered that galaxies are moving away from each other, suggesting that the universe itself is expanding. By knowing the rate of this expansion, scientists can work backward to estimate the universe's age. If Methuselah's age estimate is correct, it may indicate that our current value for the Hubble constant, and therefore our understanding of the universe's expansion, could be slightly off. Even a small error in the Hubble constant can result in a significant change in the estimated age of the universe, potentially aligning it more closely with Methuselah's age. Another factor to consider is stellar formation in the primordial universe, meaning the way stars formed in the very early days after the Big Bang. Methuselah's age suggests that stars might have formed sooner than scientists currently think, or perhaps under different conditions than we understand. Stars like Methuselah, which have very low amounts of heavy elements, a sign they formed early in cosmic history, may offer clues about the formation of the first stars and galaxies. If Methuselah is truly as old as its estimated age suggests, it implies that the conditions for star formation existed even in the earliest phases of the universe, possibly challenging or refining current theories about what the universe looked like in its infancy. By studying Methuselah in detail, scientists are working to improve age estimation techniques for stars and the universe itself. For example, researchers are exploring ways to refine measurements of the Hubble constant and examine other factors that might influence a star's lifespan and formation. These investigations could lead to adjustments in our models of cosmic expansion, helping to explain Methuselah's apparent age and, more broadly, providing a more accurate timeline for the formation of stars and galaxies. In essence, Methuselah acts as a cosmic time capsule, holding valuable information that might help resolve some of the mysteries about the universe's origin and early development. On the opposite end of the cosmic timeline lies WASP-12b, an exoplanet that is hurtling toward its demise. Located about 1,400 light-years from Earth in the constellation Auriga, WASP-12b is classified as a hot Jupiter due to its massive size and scorching temperatures. This planet orbits extremely close to its host star, completing a full orbit in just 1.1 Earth days. The close proximity subjects WASP-12b to intense heat, with temperatures on its surface soaring above 2,200 degrees Celsius, making it one of the hottest exoplanets discovered. One of the most striking characteristics of WASP-12b is its elongated shape, which has been distorted by the powerful gravitational pull of its host star. Unlike the nearly spherical shape of planets like Earth, WASP-12b appears stretched and oblong, resembling an egg more than a sphere. This unique shape is a direct result of tidal forces, the same forces that create ocean tides on Earth. However, in WASP-12b's case, these tidal forces are so extreme that they stretch the entire planet, pulling it into an ellipsoidal shape. These tidal forces are not just changing the planet's shape, they are also affecting its orbit, gradually drawing WASP-12b closer to its star in a slow but inevitable march toward destruction. The fate of WASP-12b is sealed, it is being slowly consumed by its star, a process that scientists refer to as orbital decay. Each year, WASP-12b's orbit shrinks slightly as tidal forces drag it closer to the star. This gradual demise is expected to end with the planet's eventual engulfment by the star within a few million years, a cosmic blink of an eye. Observing this process provides scientists with a rare opportunity to study the effects of intense gravitational forces and the life cycle of hot Jupiters, which are gas giants that orbit close to their stars. The study of WASP-12b's gradual demise has broader implications for understanding the life cycles of planets and their interactions with stars. Hot Jupiters like WASP-12b are believed to have formed farther from their stars and then migrated inward over time, possibly due to gravitational interactions with other planets or the protoplanetary disk. Once they reach such close orbits, they are often doomed to a fate similar to WASP-12b's, spiraling inwards until they are eventually destroyed by their stars. Studying WASP-12b helps scientists learn more about planetary migration, the forces that can drive a planet inward, and the various outcomes of such migrations. Methuselah and WASP-12b, though vastly different in age and characteristics, each contribute to our understanding of planetary evolution and stellar dynamics. Methuselah challenges our conception of the universe's timeline, pushing the boundaries of how we estimate stellar ages, and interpret the early cosmic history. Meanwhile, WASP-12b offers a glimpse into the violent endgame that some planets face when caught in the powerful embrace of their stars. Together, these ancient and mysterious planets expand our knowledge of the life cycles of stars and planets, showing us that the universe is as much a realm of cosmic birth as it is of inevitable decay and transformation. Continue to expand our understanding of what is possible in the cosmos. Some exoplanets exist in environments so extreme that they redefine the boundaries of what we understand as planetary atmospheres and surface conditions. The planets Kepler 9b and Kepler 10b are two prime examples, each pushing the limits of temperature and atmospheric composition due to their close orbits around exceptionally hot stars. These exoplanets showcase conditions unlike anything we observe in our own solar system, presenting scientists with unique laboratories to study how intense heat and radiation affect planetary matter. Kepler 9b is a gas giant orbiting a blue A-type star, and its proximity to this star results in temperatures that exceed 4,300 degrees Celsius, hotter than many stars in the universe. Located about 650 light-years from Earth in the constellation Cygnus, Kepler 9b is the hottest known exoplanet, with temperatures reaching such extremes that they surpass the melting points of many metals. This scorching heat is due to the planet's close orbit, completing a full revolution around its star in just 1.5 Earth days. The intense ultraviolet, UV, radiation from its star bombards Kepler 9b, creating conditions that are more typical of a stellar environment than a planetary one. The heat on Kepler 9b is so intense that it leads to a phenomenon known as atmospheric decomposition, where molecules break apart under the relentless bombardment of UV radiation. On Earth, our atmosphere consists of stable molecules like nitrogen, oxygen, and carbon dioxide. However, on Kepler 9b, the energy from the star is so powerful that it shatters these molecular bonds, leaving behind an atomic atmosphere dominated by individual atoms rather than complex molecules. This means that elements like hydrogen and oxygen exist as separate atoms rather than forming compounds like water, which would be impossible to sustain under such conditions. Adding to its unusual atmospheric profile, Kepler 9b's intense heat also ionizes metals within its atmosphere, creating a mix of gaseous iron and titanium. These metals are typically found as solids or liquids in planetary environments, but on Kepler 9b, they exist as hot gases due to the searing temperatures. The presence of these ionized metals offers scientists a rare chance to study metal-rich atmospheres, and the impact of extreme radiation on planetary materials. Observing how these metals behave in such an environment helps astronomers develop models for atmospheres on similarly hot exoplanets, providing insight into how radiation affects elements and compounds in high-temperature settings. Kepler 9b's extraordinary conditions make it an ideal candidate for studying the effects of UV radiation on planetary atmospheres and the limits of atmospheric stability. The planet's atmosphere is continually bombarded by radiation that would strip away lighter gases if they were not being replenished by atmospheric processes or gravitational interactions. The study of Kepler 9b has led scientists to rethink the stability and composition of planetary atmospheres, particularly around hot, young stars that emit intense radiation. As telescopes and observational techniques advance, researchers aim to analyze Kepler 9b's atmosphere more closely, seeking to understand how long an atmosphere can persist under such extreme radiation before it's completely eroded by the star's energy. In stark contrast to the gas giant Kepler 9b is Kepler 10b, a rocky exoplanet located approximately 560 light-years from Earth in the constellation Draco. Kepler 10b is notable for being one of the first rocky exoplanets discovered, marking a milestone in the search for Earth-like worlds. However, while it shares some similarities in composition with Earth, Kepler 10b's surface conditions are far from habitable. This planet orbits its star at an incredibly close distance, taking just 0.84 Earth days to complete a full orbit, which exposes it to extreme stellar radiation and causes surface temperatures to skyrocket. The proximity of Kepler 10b to its star leads to surface conditions that are likely dominated by lava oceans. The extreme heat, combined with the planet's rocky composition, means that any solid crust would be continually melted and reformed by the relentless energy from its star. These lava oceans would create a hostile, molten landscape, with temperatures high enough to vaporize rock and create clouds of silicate vapor in the planet's upper atmosphere. In essence, Kepler 10b presents a vision of a molten world, a rocky exoplanet perpetually scorched by its star, where any solid land is likely submerged under vast expanses of churning lava. One of the most fascinating aspects of Kepler-10b is how its short orbital period affects its structure and atmosphere. With a year lasting less than a single Earth day, Kepler-10b experiences extreme gravitational forces from its star, which may contribute to tidal heating, a process where gravitational interactions create internal friction and heat within the planet. This additional heat source could further amplify the surface temperatures, making the planet's environment even more hostile. Additionally, the planet's rapid orbit would subject it to a constant, intense flow of stellar wind, potentially eroding any atmosphere it might have had, leaving behind only a thin layer of gases or none at all. The atmospheric dynamics of Kepler-10b, or rather, the limited atmosphere it may still possess, offer a unique opportunity for scientists to study how rocky planets respond to extreme temperatures and radiation. Kepler-10b is a rocky exoplanet orbiting very close to its star, where intense stellar radiation likely bombards the planet continuously. This radiation can strip away lighter elements and molecules in the atmosphere over time, leaving only the heaviest elements that can withstand such harsh conditions. If Kepler-10b has indeed lost most of its lighter atmospheric elements due to this radiation, it might now only have a thin, dense atmosphere composed of heavy gases like metals or silicates in a vapor form. Alternatively, if some lighter elements still remain in the atmosphere, they could form a fragile, tenuous layer that would indicate a surprising degree of atmospheric retention despite the intense heat. Studying this possible thin atmosphere could provide scientists with valuable insights into how long such a layer could survive under extreme conditions. It would also shed light on the mechanisms that protect or sustain atmospheres on rocky exoplanets with close-in orbits, where high temperatures and radiation are the norm. By examining Kepler-10b's atmospheric composition and the effects of its star's radiation, researchers aim to better understand the evolution of rocky planet atmospheres under extreme heat. This knowledge could help determine the survivability of atmospheres on other rocky exoplanets that orbit close to their stars. Such studies not only deepen our understanding of atmospheric loss and retention but also help refine models predicting how planets like Kepler-10b might evolve over time. This information is crucial for identifying which exoplanets might retain the conditions necessary for atmospheric stability, even when faced with the hostile environments of close stellar orbits. Together, KELT-9b and Kepler-10b represent the extremes of temperature and atmospheric conditions found in the universe, providing invaluable data for scientists studying the boundaries of planetary survival. KELT-9b's atomic atmosphere and ionized metals offer insights into the composition and behavior of gas giants under intense UV radiation, while Kepler-10b's lava-drenched surface provides a window into the volatile nature of rocky planets in close orbits. These planets remind us of the vast diversity in exoplanetary environments and highlight the unique challenges that planets face when orbiting close to powerful stars. The universe isn't just filled with fascinating planets, some of its most remarkable mysteries lie within the moons that orbit these planets. In our own solar system, there are moons that boast volcanic activity, dense atmospheres, and even conditions that could potentially support microbial life. Two of the most extraordinary examples are Io, one of Jupiter's moons, and Titan, a moon of Saturn. Each of these moons possesses unique characteristics that make them stand out, capturing the attention of scientists and sparking curiosity about the diverse environments that exist in our cosmic neighborhood. Io, one of Jupiter's largest moons, stands out in our solar system as the most volcanically active body. This incredible level of volcanic activity is due to the intense gravitational interactions between Io, Jupiter, and Jupiter's other large moons, such as Europa and Ganymede. As Io orbits Jupiter, the immense gravitational pull from the giant planet, combined with the gravitational tugs from its neighboring moons, creates powerful tidal forces that stretch and compress Io repeatedly. This constant flexing generates frictional heat within Io's core, a process known as tidal heating. Unlike Earth, where volcanic activity is driven by heat from radioactive decay and residual heat from the planet's formation, Io's heat source comes primarily from these tidal forces. The result of this intense heating is that Io's interior stays hot enough to fuel countless volcanoes, producing massive eruptions that cover the surface with molten lava. Io's volcanic plumes can rise hundreds of kilometers into space, spreading sulfur and sulfur dioxide across its surface and creating colorful deposits that range from yellow and orange to red and black. This volcanic landscape is in a perpetual state of upheaval, with eruptions occurring so frequently that they continually reshape Io's surface, erasing impact craters and other features typically seen on moons and planets. In fact, Io's surface is considered one of the youngest in the solar system because its constant volcanic resurfacing prevents the accumulation of craters and other signs of age. Io's extreme volcanic activity is not only fascinating for its geological implications but also provides scientists with insights into how gravitational forces can influence a celestial body's internal structure and thermal dynamics. By studying Io, researchers gain a better understanding of tidal heating, a process that could also be at work on other moons and planets both within and beyond our solar system. This knowledge helps scientists identify potential volcanic or tectonic activity in other tidally influenced bodies, potentially pointing to places where internal heat could support conditions favorable to geological or even biological activity. Io's volcanic activity produces vast volcanic plumes ejecting sulfur compounds high above the Moon's surface. These plumes, reaching heights of up to 500 kilometers, create an ever-changing mosaic of colors on Io's surface, ranging from yellow and red to black and white. The vibrant colors are primarily due to sulfur and sulfur dioxide deposits, which give Io a unique and somewhat eerie appearance, unlike anything seen on Earth. The volcanic eruptions on Io are so intense that they reshape the Moon's surface regularly, creating a dynamic, hostile environment that seems almost alien compared to the relatively stable landscapes of Earth. One of the most intriguing aspects of Io's volcanic activity is its electromagnetic impact on Jupiter. Io's eruptions release charged particles into space, creating an electric current that flows along magnetic field lines between Io and Jupiter, forming what is known as the Io flux tube. This interaction generates intense auroras on Jupiter's poles, similar to the northern and southern lights on Earth but on a much larger and more powerful scale. The Io flux tube is a fascinating example of how a moon can influence its host planet's magnetic field and atmospheric dynamics, adding a layer of complexity to the relationship between celestial bodies. These interactions demonstrate that moons are not merely passive objects orbiting their planets, they actively shape and contribute to the systems they inhabit. Moving from Jupiter to Saturn, we find Titan, another moon that offers an entirely different set of characteristics and mysteries. Titan is unique among the moons of our solar system because it possesses a dense atmosphere, primarily composed of nitrogen with a significant presence of methane. This atmosphere is thick enough to support a weather system, complete with clouds, rain, and even surface lakes and rivers, not of water, but of methane and ethane. Titan's hydrocarbon cycle functions similarly to Earth's water cycle, where methane evaporates, forms clouds, and eventually precipitates back to the surface in the form of rain. This cycle creates methane lakes and rivers that carve into Titan's icy surface, forming landscapes that, while alien, bear a striking resemblance to certain features on Earth. The presence of these methane lakes has led scientists to consider Titan as a possible location for prebiotic chemistry, the complex chemical reactions that may serve as precursors to life. Although the methane-based lakes are inhospitable to life as we know it, they offer a unique environment where organic molecules could potentially form and interact in ways that mirror early Earth conditions. The thick atmosphere on Titan provides protection from solar radiation, further enabling complex chemistry to occur on its surface. In fact, Titan's atmosphere is rich in organic compounds, leading some researchers to suggest that it could hold clues to the kinds of chemistry that preceded life on Earth, offering a natural laboratory to study organic processes in an environment that is both similar to and drastically different from our own. However, Titan's mysteries extend below its surface as well. Scientists believe that Titan may harbor a subsurface ocean composed of water mixed with ammonia beneath its icy crust. Ammonia acts as an antifreeze, allowing liquid water to exist at much lower temperatures than would otherwise be possible. If this subsurface ocean exists, it could provide a stable, liquid environment where microbial life might survive, shielded from the harsh surface conditions. The idea of an ocean beneath Titan's icy crust is particularly exciting because it expands the scope of habitability within our solar system, suggesting that life could potentially exist in environments that differ greatly from those on Earth. The possibility of life on Titan's surface or within its subsurface ocean makes it one of the most intriguing objects for future exploration. NASA's planned Dragonfly mission, set to launch in the coming decade, aims to explore Titan's surface and analyze its atmosphere and chemical composition. This mission could provide crucial insights into the organic compounds on Titan and perhaps uncover signs of prebiotic or even microbial life. Titan's dense atmosphere and methane lakes make it a high-priority target for understanding the potential for life beyond Earth, as well as for studying how chemical processes evolve in extreme environments. The study of Io and Titan exemplifies the diversity of moon environments in our solar system. While Io is a fiery, volcanic world that interacts dynamically with Jupiter, Titan presents a colder, more chemically rich environment, complete with a weather system and possibly even an underground ocean. These moons challenge our understanding of what makes a celestial body interesting and suggest that moons, rather than just planets, may hold the key to understanding the full range of conditions that can exist in the universe. They remind us that even in our own solar system, there are environments that we have only begun to explore, each offering unique clues to the processes that shape planetary systems and, potentially, the origins of life. As we look beyond the planets and moons of our solar system, we encounter objects that defy traditional classifications and challenge our understanding of the solar system's boundaries. Among these are Oumuamua, the first known interstellar visitor, and Eris, a distant dwarf planet with significant implications for how we define planets. These objects reveal the diversity and complexity of bodies that exist at the edges of our solar system and provide valuable insights into both the nature of interstellar space and the characteristics of the solar system's outermost regions. In 2017, astronomers detected a mysterious object passing through our solar system, marking the first confirmed sighting of an interstellar visitor. This object, later named Oumuamua, a Hawaiian word meaning scout or messenger, immediately captured the attention of the scientific community, as it exhibited characteristics unlike any known asteroid or comet from within our solar system. While typical comets and asteroids in the solar system follow elliptical orbits, circling the Sun repeatedly, Oumuamua's trajectory was hyperbolic. This means that it was moving so fast and on such a unique path that it would not be bound by the Sun's gravity. Instead, it would eventually leave the solar system, never to return. This hyperbolic path indicated that Oumuamua had entered our solar system, from an entirely different star system, becoming the first known interstellar object to pass through our celestial neighborhood. As scientists studied Oumuamua, they were struck by its highly unusual characteristics, especially its elongated shape, which was unlike any comet or asteroid observed before. Based on observations, Oumuamua was estimated to be roughly 10 times longer than it was wide, giving it a stretched, cigar-like appearance. This shape is exceptionally rare among solar system bodies, most of which are either round, irregularly shaped, or slightly elongated, but nothing as extreme as Oumuamua's proportions. Such an elongated form raised numerous questions, as it suggested that whatever processes had shaped Oumuamua were not typical of those that form asteroids and comets within our solar system. Theories about Oumuamua's origin began to emerge almost immediately. Some scientists proposed that its unusual shape could be the result of tidal forces. If Oumuamua had passed very close to a star before entering our solar system, the intense gravitational forces could have pulled it into its elongated shape. This process, known as tidal stretching, can occur when a smaller body, like an asteroid or comet, comes extremely close to a much larger object, such as a star. The gravitational forces exerted by the star could pull on the object's structure, stretching it into a more elongated form. However, such a scenario would require a very specific set of circumstances, making it a fascinating but not fully satisfactory explanation for Oumuamua unique form. Another aspect of Oumuamua that intrigued scientists was its lack of visible outgassing, a characteristic typically associated with comets. When comets pass near the Sun, the heat causes frozen gases within them to vaporize, creating a visible coma and sometimes a tail. But as Oumuamua approached the inner solar system, it did not exhibit the expected release of gases or a visible tail. This behavior was puzzling because, shortly after passing closest to the Sun, Oumuamua accelerated slightly, as if pushed by a force beyond the Sun's gravity alone. Normally, such acceleration in comets is caused by outgassing, where gas and dust are expelled, creating a small but measurable thrust. In Oumuamua's case, however, no outgassing was observed, leaving scientists searching for alternative explanations. One theory to explain this acceleration without visible outgassing is that Oumuamua may have a very different surface composition than typical comets. Some researchers speculate that it could be coated in a layer of solid material, such as carbon-rich compounds, that would prevent gas from escaping. Alternatively, Oumuamua might contain volatile elements trapped within, which were released in small amounts to create thrust without producing a visible tail. Other scientists have suggested that it could be a fragment of a larger body that broke apart under extreme conditions, such as a collision or a close pass by a star, which might explain both its shape and its unusual behavior. The lack of definitive answers led to a surge of alternative theories, including the intriguing possibility that Oumuamua might be an artificial object. While most scientists agree that this idea is speculative, a few researchers proposed that Oumuamua's shape, lack of outgassing, and unexpected acceleration could be consistent with a thin, flat object propelled by solar radiation pressure, similar to a light sail. A light sail is a technology that uses the pressure exerted by sunlight to accelerate an object through space. If Oumuamua were a flat, ultra-thin object, it might experience slight acceleration from solar radiation without the need for outgassing. However, this idea remains largely hypothetical, and there is no direct evidence to support the notion that Oumuamua is an artificial probe or structure. In the absence of concrete answers, the prevailing theory is that Oumuamua is a natural fragment from a distant star system, possibly ejected during the formation of a planetary system. Just as planets and asteroids in our solar system formed from a disk of gas and dust around the young Sun, similar disks exist around other stars, leading to the formation of planets and other bodies. During this process, gravitational interactions can fling material outward, sometimes with enough speed to escape the star's gravity entirely. Oumuamua might be a remnant of such a process, having traveled through interstellar space for millions or even billions of years before reaching our solar system. The discovery of Oumuamua has opened up a new area of study in interstellar objects. Its brief visit provided a rare glimpse of material from another star system, offering scientists a unique opportunity to study the potential diversity of exoplanetary systems beyond our own. While Oumuamua has already exited our solar system, its mysterious characteristics continue to inspire theories and drive new research. Its passage reminds us of the vastness of space and the likelihood that other star systems might send similar visitors our way in the future. With advancements in astronomical observation technology, scientists are eager to detect and study more interstellar objects, hoping to unlock the secrets they carry from other parts of the galaxy. Oumuamua's behavior also set it apart from typical solar system objects. As it traveled away from the Sun, astronomers observed a slight but measurable increase in its velocity, a phenomenon known as non-gravitational acceleration. Usually, this acceleration in comets is caused by outgassing, where heat from the Sun causes frozen gases to sublimate and create a thrust effect. However, Oumuamua showed no signs of visible outgassing or a comet-like tail, leaving scientists puzzled. The lack of detectable gas emission and the object's continued acceleration led to alternative theories about its nature. Some speculated that Oumuamua might be covered in a layer of solid material, like a crust, that prevented gas from escaping. Others proposed that it could be a fragment of a larger body that broke apart under extreme stress or tidal forces, resulting in its elongated shape and peculiar motion. The mystery surrounding Oumuamua's origin has led to further speculation, with a few researchers even considering the possibility that it might be an artificial object created by an advanced civilization. While this idea is largely speculative, it has fueled popular imagination and inspired studies on the possibility of interstellar travel and artificial objects in space. The scientific consensus leans toward the theory that Oumuamua is likely a natural fragment from a larger body, possibly ejected from its home star system during a planetary formation event. However, the absence of clear answers and the lack of an observable explanation for its acceleration continue to make Oumuamua one of the most intriguing objects ever observed in the solar system. In contrast to Oumuamua's interstellar mystery, Eris is a more familiar yet equally fascinating resident of the Kuiper Belt, the region of icy bodies beyond the orbit of Neptune. Eris is classified as a dwarf planet, a category that came into prominence largely due to Eris itself. Discovered in 2005, Eris is slightly smaller than Pluto but has a much higher density and reflectivity, making it one of the most reflective objects in the solar system. Its highly reflective surface suggests that it is covered in a layer of frozen methane or water ice, which reflects sunlight efficiently. The brightness of Eris allowed astronomers to study its composition and surface properties, offering insights into the nature of Kuiper Belt objects. The discovery of Eris had significant implications for the definition of planets in our solar system. At the time of its discovery, Eris was thought to be larger than Pluto, leading astronomers to consider it the 10th planet. However, this classification raised questions about what exactly qualifies an object as a planet, especially as more Kuiper Belt objects similar to Pluto and Eris were being discovered. This debate ultimately led the International Astronomical Union, IAU, to redefine the criteria for planethood in 2006, creating the new classification of dwarf planets and reclassifying Pluto as a dwarf planet alongside Eris. Thus, Eris played a pivotal role in reshaping our understanding of the solar system and the categories of celestial bodies within it. Eris also exhibits fascinating seasonal changes that affect its surface and atmosphere. As it follows its elliptical orbit around the Sun, the distance between Eris and the Sun varies significantly. These changes in proximity result in variations in surface temperature, albeit within the range of extremely cold conditions typical of the outer solar system. When Eris is farther from the Sun, its surface freezes over completely, forming a reflective icy crust that maintains its high albedo. However, as Eris moves closer to the Sun, some of this ice may sublimate, creating a thin atmosphere that consists primarily of nitrogen and methane. This seasonal transformation is similar to what scientists observe on Pluto, where the thin atmosphere expands and contracts based on the dwarf planet's position in its orbit. Studying objects like Eris has broadened our understanding of the Kuiper Belt and the types of environments that exist at the solar system's edge. These regions are populated by icy bodies that likely contain some of the oldest materials in the solar system, offering a window into the early stages of planetary formation. Observing the seasonal cycles on Eris, as well as its reflective surface and potential atmosphere, provides scientists with insights into the processes that govern the outer solar system's dynamics. By analyzing the reflective properties and atmospheric changes on Eris, researchers can develop models to predict the behavior of other Kuiper Belt objects and even identify patterns that might hint at similar processes in distant star systems. Together, Oumuamua and Eris represent two distinct but equally compelling aspects of distant solar system objects. Oumuamua challenges our understanding of interstellar visitors, with its mysterious acceleration and alien appearance inviting speculation and pushing the boundaries of what we consider possible. Meanwhile, Eris has reshaped our understanding of what constitutes a planet and has added depth to our knowledge of the Kuiper Belt, where frozen worlds undergo seasonal transformations despite their great distance from the Sun. These distant objects serve as reminders of the vast diversity within our solar system and the complex interplay between celestial bodies, reflecting both the solar system's ancient past and its connection to the broader cosmos. If the idea of parallel universes and the mysteries of the multiverse fascinate you, imagine the possibilities of exploring realms with unique laws of physics and strange cosmic phenomena. Every theory we uncover brings us one step closer to understanding the vast, unknown realities that might lie beyond our own. If you enjoyed this dive into the multiverse, don't forget to like, share this video with fellow space enthusiasts, and subscribe for more mind-expanding content. Let's keep exploring the wonders of the cosmos together.